Okay, well, today I guess I'd like to discuss. Okay, well, today I guess I'd like to. Nice, I've got the echo going again. Discuss. Okay. Okay. So I'm getting closer to the situation. This is a little awkward not having an editor here for me. I'm just sharing my screen. So it's just to remind everybody. Wow. How to ask questions with me. So we have this Google Docs doc and document, and you can add your red check marks next to the problems you'd like to see me do for Tuesdays. And on Wednesday, I'll give this lecture. And so there was a few I didn't do last time, which is include the preview problems, which is for this week's material. And so on page 150, number 2, we've got, number 4 was asked. And so number 4 is give an example of a function describing a situation where it is bad to be increasing and good to be decreasing. So what's a situation where a function's increasing and that's bad, and when the function is decreasing, that's good? So the basic example, let me switch back to my other screen now. Okay. The basic example where that is good. So increasing is bad. Oh, this is problem number 4 in section 3.3. Increasing is bad. Decreasing is good. So several people asked that question of like, what's an example of that? And so we're asking about a function. Normally I say f of x and x, but we're talking about any function. So I could think of x as any input variable and f of x as any output different variable. So we could think of it as like this. So x could now be time, for instance. I'll make this example. And the example will be how much a company uses for costs. Like how much does it, the costs of running a company change as time goes by. So that's how much expenditures a company is going to use as time goes by. And so at different times, they're going to be spending a whole bunch of money in order to run their processes. And later, maybe in the summer months, they spend less money. So when the function is increasing, that's bad. That's not good for the company that the costs are going up. And when it's decreasing, that's good for the company's profits. That's good for their bottom line if it's happening. So a decreasing function is not necessarily negative. It's not necessarily terrible. It's not necessarily morally or value-wise bad. The function is abstract. It doesn't really matter from the mathematics point of view whether something is good or bad. The model is where the good or bad notions come in. Okay, so hopefully that answers that question. And that's the only one that had a lot of preview check marks. And so I'll skip the others until somebody asks me a question. Let's see, Luke P is saying quiz number 1. Okay. Again, if the better way to do this, because I can't read the chat very often, so I've got you this time, Luke, and so I'll do quiz number 1. But next time, please use the Google Docs form, 5 minutes before lecture, and I'll take a peek. Okay, so quiz number 1. See, yeah, I'm not ready for that. Let's see. Quiz number 1. Ooh, that's a nightmare. Okay. That's a good problem, though. This is going to take a while. Okay, so let me write that down, I guess. The problem is I have x squared minus square root of 3 times x times y plus 2y squared equals 5. And I'm supposed to find the tangent and normal lines at the point square root of 3, 2. Okay, so that's our question. Now let me move back to the screen so I can see what I'm looking at. Okay. And so if you want to see this best, I really recommend maximizing the screen. Then I can write a little smaller and you can still see it well. So now we have this implicit difference. I want to find the tangent and normal lines. So I'm really looking for what is y prime. That's the slope. And then the tangent line, I'll be able to find the equation of the tangent line, again by our normal form here, is that y minus y naught, or y equals m times x minus x naught plus y naught. And the x naught and the y naught that I put in are these two values. So square root of 3 and 2. So same thing we've been doing since day 1, right? And I just have to find out what is this slope right here. And to find the slope of the tangent line to this equation, I need to find the derivative of y. I need to see how y is changing. Again, this implicit function has some complicated graph that I don't know exactly what it looks like, but it does look like an ellipse. I just know because it's what's called analytic geometry, where you connect up the algebraic equation to the shape of the graph. And so when I see a quadratic here and a quadratic here and this, then mathematicians have just studied this, and we know the form of this is going to be a circle or an ellipse, a spread out circle, if this isn't perfectly normal. And it's not normal because the coefficient in front of y squared is different than the coefficient in front of x squared, so it's going to be squished in some way. Okay, so this ellipse here, oh, well, actually, I don't know if it's an ellipse. It could be a, just from that consideration, it could be an also a hyperbola. Anyway, I don't know what it looks like. I haven't analyzed that. I don't care, but the calculus allows me to figure out what the shape of this function is locally near this place. I can find the tangent line to this graph at that spot by finding y prime. So if I can find that y prime, I can find the slope, and I know what the shape of the graph looks like, at least locally nearby. I know what the tangent line looks like. So I can do that without any graphing, without any drawing. I can just do the analysis here. And so what I'm going to do is find this y prime. That's our big goal. And so how do I do that? Well, I just hit both sides of this equation with a derivative. And so that's going to be the job I want to do. So I'm going to throw a different color real quick. I'm just going to hit this with a DDT, or not, sorry, a DDX on this side. And I have to do the same thing to the other side to keep the equation correct. And that will help me find a dy dx. I'll help you find a y prime. Okay, so that's my first step. If I take d dx of x squared, it just becomes 2x. And then if I take d dx of this, it's minus square root of 3 times, well, now I have a product of two different pieces of x. X is a function of x, and y is actually a function of x. Y changes as x changes. So I have a product rule here. I have to differentiate. The first one is a 1. Then I leave the second one alone, plus I leave the first one alone, and I differentiate the second one. That's dy dx right there. Okay, that's just differentiating with respect to x, x times y. That's the hard part of this problem, right? As far as calculus goes. Now the algebra. Okay, and now the other piece, we have 2y squared. I have to differentiate that with respect to x. And again, it's a chain rule this time because it's a function of x squared. And so I do the outermost function first, the squaring, and it becomes 4y to the 1 power times the derivative of the inside, which is y prime. And that's it for the left-hand side. And the right-hand side is going to be derivative of 5 is going to be 0. Okay, this auto focusing is doing great. Okay, a little better. So please unmute and start yelling at me as soon as something's going wrong, because I'm focusing on the paper and I can't see anything. Okay, so when we get this derivative, I differentiated this with implicit differentiation. I've gone through here, and what we did was we found the derivative with respect to x, and in there we're automatically going to pop out a couple of different y primes, the derivative of y with respect to x. So it's here and it's here, and they're always just sitting outside, and they're always just sitting on the edge, and so I can just always algebraically pull them off, isolate them, put everything else on the other side, and then divide the coefficients in prime. So that's what I'm going to do now is the algebra on this. I'm just going to want to find the y primes. So first I'm going to move this 2x to the other side. So on the other side I have minus 2x, and now the 2x is on the other side, on the 0 side. And now I just have this stuff. And now amongst this stuff, I'm just going to factor out the y prime here and here. And then this one doesn't have that. I still have just minus square root of 3 times y plus, well, I have a minus square root of 3 x y prime plus 4y y prime. Now here I want to factor out the y and the y prime out of these two terms, and I want to move this one to the other side. So that's the next step. I just have this one goes to the other side. I add root 3 times y, and then I still have the minus 2x. Okay, and now this one's gone, and now this side I'm just keeping right here, and I'm going to take out the y prime in the same step. I'm really conserving on paper here. So if I factor out the y prime, it'd be 4y times y prime and minus 3x times y prime. And what I've achieved now is that I have the y prime isolated. There's just one y prime that I see alone in there. And so if I just divide by that, I have the answer, which is y prime equals root 3y minus 2x. That was this other side. And I have to divide by this side, minus root 3x plus 4y. Okay, if I didn't make any algebra mistakes with all the distractions, awkwardness going on with home broadcasting, then this should be the correct answer. This is y prime. So this should tell me my m. Okay, I was looking for what is y prime, what is the slope of the tangent line. That's what y prime gives me. And that gives me exactly the value at root 3, 2. So if I just stick that in there, I'm going to have it. So at root 3, 2, that's my x, y value that I want to stick in to here to find my m. And so that's it. So I have that m equals root 3, y is 2. So root 3 times 2 minus 2 times root 3 is the x value, all divided by minus root 3 times x is root 3, plus 4 times y is 2. So I get 2 root 3 and 2 root 3, and I subtract the 2, I get 0. And on the bottom, I have 8 minus 2 root 3. So it's 0 divided by a number is still 0. That's my slope. That's y prime equals m. So that's my equation. I have the equation of the tangent line is y equals 0 times all that plus 2. That's the answer for the first part. And so the tangent line at this spot is just the horizontal line, the slope 0 line. It has slope 0, so it's just straight over. And so then the normal line is perpendicular to it. In other words, it has slope 1 divided by 0. It has slope infinity or minus infinity, or, well, it doesn't have any slope. It's a totally vertical line. And so the normal line is not y equals anything. It's just the vertical line x equals a constant. Just like here, y equals a constant for a horizontal line. A vertical line is x equals a constant. And x equals a constant, which constant? Well, that's the one. Okay, so that's how you do that one. Okay, if there's any questions, I'm looking at the chat for the moment, but speak up if you'd like to hear anything or want me to explain any piece of it more carefully.
A number, I can't remember what number it was on the quiz, but where you asked to clarify the relative. Let's see, what number was it on the quiz? It's number 3. And you say find and clarify the extrema. Do you just mean the maximum and minimum, or do you mean relative maximums and minimums as well?
Yeah, so that's just a language issue, right? So find and classify the extrema of this function. And so what that means, yeah, find all the maxes and mins, and that means find the absolute maxes and the relative maxes, the absolute minimums and the relative minimums. So that's what classifying them is like saying which of those 4 options they are after you find the extrema. So yeah, this is just a definitional question that you're asking, right? It's just like, it's not my favorite part of math or any other technical field, but it's necessary to have really precise language, right?
Yeah. Thank you.
Sure.
Building on that question.
Mm-hmm.
So for, absolute maximum and minimum, I think the textbook said that they also count as relatives.
That's right.
Both relative and absolute. So if you were grading us as far as giving the answers, would you want us to list the absolutes also as relative?
No.
Okay, cool.
Yeah, I mean, I'm picky about some things and not on others. So that's tough to sit in a math class, right? Yeah, I mean, but a pickier teacher would say.
Yeah. That. So like for the question on the quiz, there was like 4 points, that 2 absolutes and the 2 relatives.
Mm-hmm.
And so I just labeled them one of each.
Yeah, that's fine.
Cool.
Yeah, I mean, if you say it's an absolute max, then it goes without saying that people should know it is also a relative max if it's an absolute max. But there can be only one absolute maximum value. I don't want to confuse you by saying it can happen at 2 different places, but it's true. A function can have an absolute maximum value, but it can hit there in several different places. Like the sine function has an absolute maximum value of 1, but it happens at infinitely many places as it bounces up and down.
That makes sense. So would you just have to give a function for that? Or how would you list that for a sine function, for example?
So
Absolutely.
like saying, where are the maxes?
Hmm.
Well, so I'll write it down. So the max of the sine function is 1, and it occurs at x equals, well, it occurs, the sine function has a maximum at pi over 2, right?
Yep.
And then it has it at 3 pi over 2, and then it has it at 5 pi over 2. So I can say it like this. Dot, dot, dot. But then I have to go back to, sorry, yeah, that's right. And then so at minus pi over 2,
Hmm.
and all those. So that's one way of saying it. Computer can't understand dot, dot, dot yet. I mean, they're getting better. But this is sort of just a pattern. And then people figure out, I mean, the odd powers. So the better way to say is, or you can say it's at x equals 2n plus 1 pi over 2.
Cool.
Which means the odd powers of pi over 2 for all n in Z. So for all integer values of n, you put an integer in there, and that's going to be one of the places, that you hit. It's not an extreme, that I'm wrong. So I did it wrong, right? Because I was just doing it off the top of my head. It's
Yeah,
not the max.
that's the min.
Well, it could be a max here, and then it's a min here, then it's a max here. And then
Oh yeah.
I did all the extremums. So
Yep.
the absolute extrema of sine of x is plus or minus 1
Yeah.
at these spots. So that's the sort of thinking you want to do when you write them down. But
Got it.
in this class, we're not being nitpicky about this. This is way too early to care about such things. But when you take even discrete math and you start doing things like this with this upside down A, and I'm not doing that in this class, but
Okay, thanks.
you bet. Okay, so let's get to the lecture then. People might want to skip to this spot if they're only tuning in for the lecture on the YouTube. So I do have a few people here on speaker view, but still, it's not the entire class. So I do want to ask people to email me if there's a better time to have this lecture. I know some people are still working, and so I really want to make it as accessible as possible. So I'm thinking of maybe Thursday evenings is just another option. So message me if you have a better time in place here. Okay, so let's actually get to the lecture, unless there's any other questions. And so we're talking about section 3.3 and 3.4. Okay, so well, section 3.3 is going to be over the first derivative. Basically, it's going to ask, what does the first derivative tell us? Now, we've been studying this all semester long. The second one, 3.4, is going to talk about the second derivative test. And so this is going to be the challenging part of today, because we really have not been talking about the second derivative much at all. Whereas the first derivative, we've talked about that from day one every single day. And we've learned that the first derivative tells us about where the function is increasing and decreasing, because that's where the first derivative tells us what the slope is. And if the slope is positive, that means it's angled up. It means the rise over the run is positive. The rise is positive as you run over 1. So the function is increasing. And when the first derivative is negative, when the first derivative is negative, then that means the slope is negative. That means the rise over the run is, well, as I run over 1, the rise is actually negative. So that means it's decreasing. Okay, so this is something that should be very comfortable and familiar for everybody right now. The first derivative tells us where it's increasing and decreasing.
Do you need to know if it gets fuzzy or not? Is it
Yeah, please.
not that fuzzy, but
Nah, it'd be better if it would give me a better choice here, but look at that. Okay. Yep, stop me every time that it gets irritating. Okay, so where the function is has a first derivative that's first derivative is positive, then it's increasing, first derivative is negative, then it's decreasing. And that tells us everything you want to know about the function. That basically, if your function looks like this, if this is my x and this is f, then my first derivative tells you where the function is increasing or decreasing, because where the first derivative is positive or negative. So the first derivative is the slope of the tangent line. So at this spot right here, the first derivative is 0. And at this spot right here, as I go down, the first derivative is 0. And in between, is it positive or negative? That's sort of our question always. I only found the places where it's 0, and now everywhere else, it has to be either all positive or all negative between the spots where it's 0. And so in this case, the slope was 0. Now the slope is positive all the way through here. And so that's what the first derivative looks like. And where the first derivative is positive, then that's where the function is increasing. And over here, the first derivative is negative. So that's where the function is decreasing. The function is that the maximum point has slope 0, like that. And so now, as I move over here, the slope keeps angling down. The slope gets more and more negative. So I draw that as the slope getting more and more negative. And over here, again, the slope is negative until it goes to 0. So I have negative slope over here, and it gets less and less negative as it angles down like that. And so it gets less and less negative, and then it hits 0. Okay, so the second derivative, the first derivative is going to look like this. And the first derivative, where it's positive and negative, tells us where the function is increasing and decreasing. That's very powerful. And that also leads to the first derivative test that says a place where the first derivative equals 0, like this, that x star, okay, that special x, if the derivative is first derivative is 0 and the derivative is positive for x less than x star nearby, and if f prime is negative for x greater than x star over here, so if the derivative is negative over here and the derivative is positive over here. Oh, thank you.
Yeah.
So if the derivative, so here's the first derivative test. If the first derivative is positive to the left and negative to the right, so for the x value is bigger than x star, and for the x value is less than x star over here, if the first derivative is positive, then what does that tell us? It guarantees that x star is where a max or a min occurs. Well, it's a maximum. Okay. So where the derivative changes from positive to negative, and right at that 0, then this spot is where the maximum occurs. At x star, that's where the maximum occurs, and that is the maximum right there, that height. And then the reverse. I don't want to write it all out. It's just, and vice versa. It's written out in your book that in the other case, if the derivative is positive for x bigger than x star, and the derivative is negative for x smaller, if I switch these two, then I get a minimum. So in other words, where at this minimum value, where the derivative goes from less than 0 to greater than 0, that's where I know this function is going to have a minimum. Okay, so that's the first derivative test, and that's powerful because often when we take a derivative of a function, it gets a little bit simpler in mathematics. But also sometimes you know something about the derivative, you don't know something about the function. And so if you know about the derivative, then you can find the maxes and mins of the function. Okay, that just happens a lot in applications. Again, one simple application is when you're running a rocket into outer space, then you know something about the fuel you're hitting it. In other words, you know about the acceleration. You know how you're going to affect its second derivative. You don't know how it's going to respond unless you integrate that second derivative, unless you find the antiderivative. Okay, so if you, in applied math and when we go to Calc 2 and etc., you often know more about the derivatives than you do about the function. Okay, so that's the thinking behind all this, but that's for later.
Professor?
Yep.
When we have, would that also tell us where turning points are?
Yeah.
Could
So
what if there are more than 2 zeros of the first derivative?
well, there can be infinitely many zeros.
So the f prime of x you have there, you have equals 0. And then you're saying what, that for x that's less than, because I'm wondering how it would work if you had more than, 2 zeros. What if you had 30?
Yeah, so like the sine function, it just keeps oscillating forever, right?
Mm-hmm.
And so there's infinitely many places where there's maxes and mins. There's infinitely many zeros.
Yeah.
In that case.
So how would you know that something's, oh, so it would still be a max. It just means, so in any kind of function where we're using this test, if we get more than 2 zeros, then we know that it oscillates at some point where it goes back and forth.
Yeah, that's true.
Okay.
Unless there's a discontinuity somewhere.
Okay.
But anyway, typically no, that's exactly right what you said. But also these are for a relative max is all we're going to find out from the first derivative test. So let's do an example. Okay, let's do example 3.3.1 in the text and illustrate the first derivative test. So that's our first step. And so let's do example 3.3.1. And this one is f of x equals x cubed plus x squared minus x plus 1. And my job is to find the intervals where f is increasing and decreasing. So where is f increasing and or decreasing? Okay, and then when I know where it's increasing and where it's decreasing, I'll be able to find the second question. First question would be, where is it increasing and decreasing? Well, where are the maxes and mins? Okay, so this first part will tell me what the second part is. And so that is basically what this first derivative test is. And so that's what I'm going to use on it, is I'm going to find where the derivative is positive, then the function is increasing. And where the derivative is negative, I'm going to find where the function is decreasing. And so that's what I just need to do, is do a little bit of algebra after I've done the calculus. So here's the answer. Well, take the derivative. The first derivative tells us the answer to these two questions. First derivative is, well, easy, right? For polynomials, derivative of x cubed is 3x squared. Derivative of x squared is 2x. Derivative of x is 1, and the derivative of 1 is 0. So that's our first derivative. And that's enough to tell us everything we want to know. Later, we're going to take the second derivative for the second derivative test. The second derivative test is just another test. The second derivative also tells us where things are happening. And it's just another tool for us to understand functions. So we're going to do all this, by the way, is a lot of stuff to take in, but we've done this first derivative stuff since the first day of class. And next week, we're also going to do curve sketching and talk about the first and second derivative test again. So that's our first derivative. And here's the whole step. Is step one, I want to find where is the first derivative? 0. That's here and here in this first example. And where it's 0 will tell us, well, the intervals on which it's going to be all positive or all negative is going to be the intervals between them. Okay, and so I set this equal to 0 is the first step. Then take your derivative and set it equal to 0 and solve for x. So when I solve this for x, well, I don't know. Okay, I don't like polynomials with a 3 in front of them. So I don't know, did they give me an easy problem or not? I haven't done it. Maybe I can factor this thing. And so I'd have 3x squared. I need a plus 3, right? So plus 1 minus 1. I'd get plus 3x, and then minus x is 2x, and then minus 1 times plus 1 is minus 1. Okay, so they were easy on me. Again, I always want to remind you, this is math class where the teachers are giving you problems that you can do in your head. In real life, the problems never factor so simply. I mean, 100% of the time, that's not it. If I round up from 99%, it's 100% of the time, that doesn't happen. They're always, when you go into real life, you're gonna get 3.1 and 2.6 and minus 0.8. And those don't factor, okay. Okay, but anyway, back to pretend world of math class, that I can find where this thing is equal to 0. And we can always find that in the real world too. It's like, where is this thing 0? I use a numerical method. Here I'm using an analytical method. I'm actually just figuring it out with my head in my basement. Okay, so what we've got going on is that this is gonna be 0, where x makes this one 0, or this one 0, because 0 times anything is 0, and 0 times anything is 0. So where this one is 0 is minus 1. Where this one is 0 is 1/3, because 3 times a third is 1, minus 1 is 0. Okay, so those are my two spots that in this previous spot would look like that. But now we know that it's on this number line at 0, at 1, and at 1/3. So at minus 1, I have a 0. And at 1/3, I have a 0, is where the derivative is 0. Not where the function is 0, but where the derivative is 0. Where the derivative is 0, that tells us where the function is flat. And those are going to be possible maxes and mins. So these are my spots. The only other place I can have a max or a min is where the derivative doesn't exist. And this derivative exists everywhere, so this is it. These are my only places I can have a max or a min. And so that's my first derivative test, is that if the derivative is 0 and I have these pieces, then I can get it. So now the next step is just in between here. Is this a positive or is it a negative? And then after here, on this interval, from 1/3 forever after, is it a positive or is it a negative? That's the question I have to ask between each of these intervals. And finally, on this interval, is it positive or is it negative? Okay, so is the derivative positive or negative? So how do I decide whether or not the derivative is positive or negative between minus 1 and 1/3? Well, I just stick in any value between minus 1 and 1/3 into the original derivative here to find out if the derivative is positive or negative. So I'm going to stick in the easiest one I can think of, and 0 is my favorite number to calculate with. So I'm going to stick in 0, and I check f prime of 0, and I figure out is that positive or negative. And f prime of 0 is 0, 0, it's minus 1. So it's negative. So my answer is that my derivative was negative in this case at 0. The derivative is negative. So it's 0, or it's negative all the way through here. At 0, it's negative. That means it has to be negative everywhere else between -1 and 1/3, because again of the intermediate value theorem. The only way it could switch between minus to plus is if the derivative ran across the x-axis here. If it hit 0, and it's not going to hit 0 between here and here, because these are the only places it hits 0. So it has to be minus the whole way through. Same thing with this one now. Intermediate value theorem says I just check it at one value at any of these places. So I am now going to check a value over here. Any number bigger than 1/3 is going to have the same value of derivative as all the other numbers bigger than 1/3. So I'm going to check f prime of something bigger than 1/3, and my favorite number is 1 to calculate with after 0. So 1, when I stick it into f prime of 1, will give me 3 times 1 plus 2 times 1 minus 1 is 5 minus 1. I get 4. So the derivative is positive here. So we've answered that question. I answer this last question. It's going to be negative. Why? I already know, because of algebra. That this derivative here looks like this, and at x equals -1, it's a first order 0. So this function is going to switch from positive here to negative here, and then from positive it's going to switch to negative like that. So my first derivative is going to look like this. In fact, that's what this is a parabola, and it looks like that. That's what the derivative looks like. Okay, so that's all the analysis of the derivative. Okay, you take your derivative, find where it's 0, find where it's positive and negative, and then you're going to be able to know with the first derivative test here what the maxes and mins are. So now with the first derivative test, I can just look at this graph and know that the answer to this question of part B, of where the maxes and mins are. So part B just says the maxes and mins are going to be here and here, my only possibilities, and the endpoints, but there are no endpoints in this question. And so I just look at that one, and the first derivative test tells me that this is going to be a max or a min. So which is it going to be? Well, I just look at it. The first derivative is negative. That means the slope is negative, means the function is going down. Then it hits 0 derivative, and then the derivative goes positive, so the function starts going up. So it's decreasing where the derivative is negative, it's flat, then it's positive. So that one's going to be a minimum. And this one, for the vice versa reasons, for the reverse reasons, this one's going to be a maximum. It went from positive derivative like this, then it's flat, then it's going to be going down, according to this.
I have a question about that.
Yep.
So from your first point there where you mentioned the minimum, you've got the slope, or maybe I'm not reading this correct, but when you circle the minus, the slope is going downward. Then after the minimum, you've signified that the slope is still going downward. And then
did I say that wrong? Oh, wait. I screwed this whole thing up for the last 5 minutes.
Yeah, like, right? Shouldn't that be?
Yeah, I screwed this whole thing up for the last 5 minutes. Sorry about that. I got too excited about it's gonna switch. I circled that it's positive here and it's negative here, and then I circled that it's negative, right? And I said it was gonna switch. I don't know why I said it was gonna switch. I just looked at this positive. So it switches from positive to negative. It's gonna switch back to positive. Okay, so no, it's not negative. Maybe I need another color here.
Use this to illustrate something though. If we did have two negatives, then we would know that what is going on there.
Yeah, if I did have two negatives, how could I go from negative to negative?
It doesn't have a minimum there then. So would that not be possible?
No, it's possible. It can go from negative to negative, negative slope to flat to negative slope.
You could still have a minimum or a maximum then because of that slight dip, or?
Nope, it wouldn't be a min or a maximum.
It's just neither.
So what I've drawn here, if it was negative to negative, it would look like that and then down. And that is not, that's a flat spot where the tangent line is flat, but it's not the smallest spot because it goes lower, and it's not the biggest spot because it goes higher.
Is
And
that
then-
what they call a saddle point?
Yeah, the saddle points are exactly what happened here, but you talk about saddle points in higher dimensions. So when you get to calculus 3, you're going to be talking about surfaces, like two-dimensional surfaces. And then with inputs of x and y, then you can get a saddle point of slopes down this way and slopes down this way. So slopes up, slopes down, and you get a saddle point. So in one dimension, I would never call this a saddle point. It happens to be an inflection point, which we'll talk about in 10 or 20 minutes. Okay. But it's, some people might call it a saddle point, sure. Okay, so I screwed this up, so let me try to backtrack a little bit and try to justify this, try to clarify it. So it's not negative here. If I should have checked it, I checked it at 0, it was negative. I checked it at 1, it was positive. I should have checked it at some number smaller. So let me check the derivative at some number that's smaller than -1. So what number is smaller than -1 that you want to check it at? Well, -2 is, you want some whole number is easy to calculate with. So, but I could check any number smaller than -1. I could put -200 in there if I wanted. If I put -200 in there, the calculation gets bad. Okay, but derivative at -2 is 3 times -2 squared is 3 times 4 is 12. -4 is 8. -1 is 7. So this thing is positive, not negative. I screwed it up. I want to circle the positive here. Okay, so it goes from positive to negative to positive. I don't know why I drew the blue line here like that. I said it's negative and then I drew it as positive. Okay, bad mistake. The function's f derivative is really positive here, it goes negative here, and then it goes positive here, like that. Okay, given that fact, given that the function is positive slope, that means the function, the original function f at the top, has slope positive back here. It looks like that. And as I get to x equals -1, then the slope decreases less and less slope until I get to 0 slope. And then it decreases even more to get negative slope. And then it gets to negative slope here is maximum negative, and then it's gonna get less and less negative until I get to here. I get 0 slope. And then as I get larger, I'm gonna get larger and larger larger and larger slope as I go positive. So the derivative here tells me the slope. In other words, the angle of the tangent line, right? And so that angle is gonna be positive, then 0, then negative. That means this spot will be a max. I'll have a maximum at that spot. And then at this spot, I'm gonna have negative slope, then 0 slope, then positive slope. So this place will be where a min occurs. A minimum will happen there. Okay, so now let's answer our questions. Okay, that was the analysis. This is the first derivative test, and that is how you do this whole thing. But now how do I just write down the answer? So the first derivative is this. We calculated it. We set it equal to 0. I solved where this first derivative is 0 is here at -1 and 1/3. And then I found between -1 and 1/3 whether it's positive or negative, positive, negative, or positive, negative. That's all. And that tells us everything now. And what it tells us is for part A, f is increasing where? So it's increasing on the interval where the derivative is positive. And that's here and here. Increasing, not that one. Okay, I need round brackets. It's increasing from -infinity until I get to -1. So all the way from -infinity all the way to -1, the function f is increasing because this derivative is positive. It's also increasing on this place where the derivative is positive. So from 1/3 to infinity. Okay, f is decreasing everywhere else where the derivative is negative. from -1 to 1/3. Okay, and that also tells us where the maxes and mins of f are. F has a min of f of something at x equals 1/3. At x equals 1/3, the derivative switched from negative, so it's decreasing function, to 0 to positive. So that's what this first derivative test tells us. And f has a max of f of, okay, so it's f of 1/3, by the way. So f has a minimum of f of 1/3 at x equals 1/3, has a maximum of f of -1 at x equals -1. So the first derivative test, let's look at that one more time. The first derivative test tells us that x equals -1 will give us a maximum value for f when I stick in x equals -1. So again, if the first derivative test says if the derivative is 0 at that special spot, at that critical number, if the derivative is 0, and if the derivative is positive to the left of the critical number for x less than the critical number, if the derivative is positive, and if to the right for x greater than x star, if the derivative is negative, which is what we have, then x star is where a max occurs. Okay. So that's what I'm using here on the first derivative test. So when you do your calculation, when you do your quiz, when you do your final exam, this is what I'm looking for, is this picture right here. If you're doing the first derivative test, you want, and messy as that is, you're looking for where the derivative is 0, mark those spots, and then you say where it's positive, negative, or positive, okay, in between those spots. So that's the whole process. The hard part is the thinking about it, is understanding what the derivative means. The derivative means the slope. That's the beginning and end of that. And next we're going to talk about the second derivative. Okay, so the first derivative is easy, but this test is going to be illustrative of how we're going to do the second derivative test too. So any questions before we go on to the second derivative test?
Yeah, something about where your critical points are for where you marked where the slope is, or where the function is increasing and decreasing. So at -1 and 1/3, you've indicated that it's both increasing and decreasing.
Oh, I see what you're saying. F is increasing at, you're saying because of the square brackets?
Yeah.
You're in here. Okay, first off, don't worry about that for the test. I'm not going to be grading you on that nitpicky problem. So this is just a philosophical question.
The concept of it.
Yep, so I'll talk about this philosophical question, but for everybody else who's listening, you can not worry about this philosophical fight here. This is correct. Okay, if you put round brackets on, it's fine. F is increasing on that spot, but it's also increasing on this. F is increasing all the way from -infinity to -1. If I take two different numbers in this interval, any two different numbers that are different, including -1 and anything else, then if the first number is smaller than the second number, then the function is smaller on the smaller number and it's bigger on the bigger number. So it's increasing all the way on this whole interval. Now, here's your complaint. Well, it's decreasing. So it's decreasing from -1 to 3. For all the numbers in here, it's decreasing. So that's how we talk about decreasing. A function's not increasing or decreasing at a point. It has to be increasing or decreasing on an interval. It has to be increasing or decreasing relative to two different points, like where the function gets bigger and smaller. So there's no such thing as whether it's increasing at -1. Well, it's increasing at -1 all the way to -infinity. Okay, so that's just how we talk about it. It's sort of technically wrong to say it's only increasing at -1. It's not, and it's increasing on the whole interval. And so that's why we put the square brackets around it. I don't want to fight about that, so I don't want to grade anybody about that. So I'll be okay with round brackets, but so it's just a minor point.
Yeah, but that concept's really helpful, actually, that it's between 2 points and not at a given point.
Mhm.
Thanks.
Yeah. No, and it's such an interesting question to a mathematician. That's why I'm wasting the extra time, even after you've given up and.
No, I like that.
Bugging me.
It helps to, I just want to understand the concept of it, and your explanation actually makes that more clear. So it is helpful.
Well, then you're at least as good as a mathematician, so you can even ask that question, right? That's a good thing. Okay, so any other questions before we go on to second derivative test? Okay, so now we're going into 3.4. So all the way back here, 3.4, the second derivative test. Let's jump there, and I'm going to do the same sort of thing. Okay, I'm going to do this first derivative, the second derivative. This is basically the abstract. This is an abstract thinking right here. I'm just doing an arbitrary function, and then this stuff is actually a concrete problem because I've actually written down the exact formula and then analyzed it. Okay, so this is just general hand waving thinking right here, and that's what I'm going to do. And then I'll do a concrete problem again with the second derivative. Okay, so the first derivative tells us about increasing and decreasing places for the function. So what does the second derivative tell us? The second derivative is going to tell us about the concavity of the function. So I'm going to notice that this is concave up in this spot. This is concave down. And so what the second derivative is going to tell us is where, okay. This is as deep and difficult as math gets, believe it or not. Now, we're only in our first semester of calculus, but the second derivative is as complicated as it gets. We don't go to the third derivative. People talk about the third derivative with the jerk and things like that. Okay, nobody really uses the third derivative. If you understand the second derivative, you understand everything. This is as deep and difficult as math ever gets. You just do it in higher dimensions and more complex situations, but the second derivative is enough for everything. And that's why when you're in physics, Newton's second law is that force equals mass times acceleration. And that basically is the law of all of science. It's like if you understand the forces at work on something, then that's it. You are only going to worry about that. That tells you everything you need to know about the model. And the forces are just the mass, which is just some scalar, usually a constant, times the acceleration. And the acceleration is the rate of change of the velocity. The velocity is the rate of change of the position. So the acceleration is the second derivative of the position. So that's it. That's all of, not just physics, it's all of science, that we just study the forces at work in a system. And so we're only ever going to go to the second derivative for most applications. So that's the hard part. It's the day we really have to grapple with what is the second derivative. And the first derivative tells us where the function is increasing or decreasing, where it's positive, negative. The second derivative tells us where the first derivative is increasing or decreasing. Oh,
We lost an
Just
image.
happened. Just right now. Yep.
Yeah, this is going to be an issue, probably. At some point, I might have to switch. Okay, but we're back. Okay, so let me repeat this again. I'm going to repeat this on the next page, what the first derivative does, and then I'm going to do the second derivative underneath it. And just, we really have to grapple with what the meaning of the second derivative is. Okay, so now we're in 3.4, is that right? Or 3.4. Basically the second derivative test, what the second derivative means. Okay, and so first I'm going to do this abstract to talk about the ideas. In other words, I'm just going to graph some function, right? So this is my function f, and here's my x values. And then I want to know, well, what does the first derivative look like? Well, again, just like as we did last time, where the function is flat at a minimum right here, The first derivative is 0 because the slope is 0. And again, right here, I've got this spot. So the derivative is 0 here and here at those x values. And in between, this derivative is going to be negative because the slope is down. So this is what the derivative is going to look like, its graph, between those two spots. So these are where I'm really looking at. And this is one of the problems on the midterm, right? And it's also going to be one of the problems on the final is like, I give you the function, graph the derivative, graph the second derivative. Okay, so now here, the derivative is positive. So I'm going to have to draw the function, this derivative function as going up that way. And over here, the derivative is positive also. So this is what the derivative looks like. The derivative, again, where it's positive means the function's increasing. Where it's negative means the function's decreasing. Where it's positive, the function's increasing. So in between increasing to decreasing, I have a maximum. In between decreasing to increasing, I have a minimum. That's the first derivative test. So now we're going to do the second derivative. And what does the second derivative mean? Well, the second derivative is the derivative of the first derivative. So I just now do the same process down here. I look to see where's the first derivative got a flat spot. And at that spot, the second derivative is 0, where the first derivative has a flat spot. So where the slope of the first derivative is 0, then that's where the second derivative is 0. Over here, and that's the only place, there's only one place where the second derivative is 0 for my function that I've drawn so far. And to the right, I just ask, is it positive or is it negative? Is the second derivative positive over here? Well, the first derivative is increasing over here. First derivative is increasing, which means that the first derivative slope is positive, which means the second derivative has to be positive then. So it's going to look like that. And over here, same thing, where the first derivative is decreasing, the first derivative slope is negative. So where the first derivative slope is negative, I draw the second derivative as negative because the second derivative is the slope of the first derivative. Okay, so all I did was this step to here, I did from this step to here, same thing. I took the derivative, and that's all that we have. So it's negative over here and positive over here. So now we got to ask, well, what does it mean? Okay. What does the second derivative mean? Second derivative means that, well, it means the first derivative is increasing here. And the second derivative being negative means the first derivative is decreasing. So what does it mean for the first derivative to be increasing over here? So if f double prime is positive, is greater than 0, then the first derivative is increasing. So what does the first derivative increasing mean? The first derivative getting bigger means that as I follow along from here along, the first derivative is increasing. The first derivative was going from a negative slope to a positive slope. The first derivative was switching like this. At this spot, f is concave up. So when the second derivative is positive, the first derivative is increasing and the function is concave up. It's shaped like a bowl sitting up like that. That's it. That's that's everything that I said is the deepest thing that is all science. The deepest thing you're ever going to see in quantum mechanics and everything else, like the deepest idea is the second derivative. It really is. And all it is there is that it talks about the geometrically, it's pretty simple. That the second derivative just tells you where the function is shaped up, concave up like that. Okay. And where the second derivative is negative, then it's concave down. That's the rest of it. So where the second derivative is negative, if I look at this spot here, from here back, the second derivative is negative. So on this interval, the first derivative is decreasing. First derivative is dropping until I get to that spot. Then later it's increasing. So it's first derivative is decreasing on the interval behind here. If the first derivative is decreasing, that means the slope is decreasing. That means the slope, as I go from left to right, the slope was positive and now it's going negative. So I have this place here all the way from here to here where the slope is decreasing. The slope is going from positive to 0 to negative. Where the slope is decreasing, f is concave down. And that concavity of the function is the second derivative's sign. Okay, the sign positive means that the function is concave up. Sign negative means the function is concave down. So concave down means it looks like a bowl going down. So quick quiz question is this one concave down or is this one concave up? This one
I'm
is,
gonna guess concave down.
yep, this one is concave down. So I'm going to call it CCD. Okay. And what's this one? What's this shape right now? Concave up.
Concave
or
up.
concave down?
Up.
This one's concave up. Okay, now I'm gonna do a quick trick question. Okay, is this one concave up or concave down?
Up.
Down.
That's what I wanted to hear. I wanted to hear both of you disagree. Yeah, there's only one answer that's right, and it's
It's going
confusing.
left to right.
Yeah, from left to right, it's decreasing, but the concavity is up.
It just
Yeah.
broke.
We
the
lost your
video.
image again.
Oh, sorry. Yeah, I'm going to have a 2-minute break in a couple of minutes because the battery is dead and I have to use a different piece. Okay, so this one is actually, to finish the punchline, that's concave up. Even though it's going down, it's concave up. The derivative is going from very negative to 0. The derivative is increasing, even though it's going from negative derivative to a 0 derivative. So because the derivative is increasing, this is concave up. So any part of the bowl here is all concave up. Any part of the bowl when it's on its upside down is concave down. So this last piece that I would do would be this one. Okay, so the last quiz question here is that concave up or concave down? And it's confusing, right? So anybody want to hazard a guess on this one?
Concave down.
Down.
Yeah, okay. So maybe you're getting the trick question here, right? This is concave down, even though it's going up. That's not what I'm asking. I'm not asking if it's increasing. I'm asking if the second derivative, what's it doing? I'm asking if the slope is increasing, and the slope is actually decreasing. The slope is dropping. So wherever the slope is decreasing, then it's concave down. Okay, so that's the tricky part. So it's concave down both here and it's concave down there. It's concave up here and concave up there. Okay, so that's just a tricky thing. But see, the second derivative just tells us the answer. So that's the cool part of science and math is computers can do it, right? Once you program it in, it's good to go. Okay, so let's actually do not just an abstract example here. Let's do a concrete problem. And well, I just want to do the same one. It's basically 3.3.1, but the book didn't do it with the second derivative test, okay? But let's do it because we already have it. F of x is x cubed plus x squared minus x plus 1. And so our part C of this question is, I basically want to find concavity, the intervals of concavity. And then part D, we'll use the second derivative test to classify the extrema. Okay, marker's dying. Everything's breaking. Let's see. So use the second derivative test to classify the extrema. I'm looking for the maxes and mins again. So before we do this whole problem, I guess I should talk a little bit about the second derivative test. Well, the second derivative tells us whether it's a max or a min. If we look here and we just see that the second derivative being positive means it's concave up. So if I find a critical point, critical points, the places where the derivative is 0, are the possible places where I have a max or a min, right? So it's the possible places where the original function is either a maximum or a min, is where the first derivative is 0. So these guys are the critical numbers, or the critical values, the critical points. These two guys right there is where f prime equals 0. Okay, and so if I find the places where f prime equals 0, if I look at a place where it's 0, and I find that the second derivative is positive there, if I find the critical number and the second derivative is positive there, that means it's concave up at that spot. If it's concave up, that means that I have a bowl shape sitting right side up. That means I have a minimum, right? So where the second derivative is positive and the first derivative is 0, I have a minimum. I have a local minimum. I have a relative minimum. And that's the second derivative test. Yeah, that's the whole thing, because the other one's just vice versa. If you have a first derivative is 0 and second derivative is negative, or the first derivative is 0, if the second derivative is negative, then we have concave down. And where it's concave down, I have a bowl shape upside down, I have a maximum. So it's a little bit confusing because the whole second derivative test is find the first derivative equals 0. If the second derivative is positive, then I have a minimum. If a place where the derivative is 0 has second derivative negative, I have a maximum. So negative second derivative means a maximum. Positive second derivative means a minimum. That flip of what you might expect. You normally think positive means max, negative means min. Well, that's wrong for the second derivative test. It's the exact opposite. So that's confusing, but it is what it is. So when I ask to do the second derivative test, you have to make that flip inside your head. You have to realize that positive second derivative means concave up, which means the bottom of a bowl. Okay, so now let's do this, and I'm probably going to get stuck in the middle with my battery dying. So look forward to that. Okay, so if I'm going to find the intervals of concavity and then use the second derivative test for this thing, I have to take the second derivative, which means I first have to take the first derivative. So first derivative is 3x squared plus 2x minus 1. And then last time we're going to need to know where this derivative is 0 to find the critical numbers. So I'm going to factor that just like we did last time. It was 3x, I think it was minus 1 times x plus 1. I set that equal to 0, and I get x equals 1/3 and minus 1 are my critical numbers. Okay, so that's what we did last time. And now this time I'm going to use the second derivative test here on these two critical numbers. First, I'm going to find the intervals of concavity, but in order to do that, to figure out where it's concave, I need to figure out what the second derivative is. Where the second derivative is positive, it's concave up. Where the second derivative is negative, it's concave down. So take the second derivative of, well, that's the derivative of the first derivative. So we get 6x plus 2. So the first derivative is 3x squared plus 2x minus 1. Second derivative is 6x plus 2 minus 0. Okay, now to find the concavity, the intervals of concavity, this one's concave up when it's positive, and it's concave down where it's negative. So to find the intervals of concavity, so to do part C and find the intervals of concavity, I'm going to find the interval line of where the second derivative is positive or negative. Okay, in order to figure out where the second derivative is positive or negative, I need to find out, well, where is it 0? Okay, and so I set the second derivative equal to 0, and then I find x equals minus 1/3. If x equals minus 1/3, I get minus 2 here, plus 2 is 0. So minus 1/3 is our special spot where the second derivative is 0, and nowhere else is the second derivative 0. So it's either always positive or always negative to the right by the intermediate value theorem again, or always positive or always negative to the left. So which is it? I have to figure out which of these 4 choices I'm going to circle. And so I just check any number bigger than minus 1/3, like 1,000. 1,000 is bigger than minus 1/3. And 1,000, 6,000 plus 2 is 6,002. That's a positive number. Okay. And any number smaller than minus 1/3, like minus 1,000, I put in x equals minus 1,000, I get minus 6,000 plus 2 is basically minus 6,000. Okay. And so the second derivative is negative here and positive here. So if it's negative, is this concave up or down? If I take the second derivative and it's always negative, that means the first derivative is decreasing. Okay, first derivative is decreasing, that means it's concave down on that spot. And on the right, if the second derivative is positive, it means the first derivative is increasing. So it is concave up. Okay, so that's it. That's the answer to part C, is that.
And the screen just died.
Okay, thank you. So I now have to sign in with this other camera. And so it'll be 2 minutes. Sorry about that. All of my equipment isn't top-notch stuff, so let's see. Next time I'll use this camera instead. Okay, back in business. Roughly. Okay, so to recap what we did, in looking at this function, I want to know where is it concave up, where is it concave down. That'll help me test where is the maxes and mins using the second derivative test. If I'm concave up at a critical point, I'm going to have a minimum. If I'm concave down, I'm going to have a maximum. So first I'm going to find concavity. So to find the concavity of this function, I take the first derivative, then I find the second derivative. When I find the second derivative, all the way down to 6x plus 2, that second derivative is either going to be positive or negative at different spots. This one's simplified all the way down to just a linear function. So it only has one place where the second derivative is 0, and that's at minus 1/3, when x equals minus 1/3. So on this x-axis here, the second derivative is 0 at x equals minus 1/3, and it's the only place it's 0. So everywhere else, it's going to have one value of positive or negative on either side. We just check the number to make sure it's positive all the way through here. That means second derivative is positive, means the first derivative is increasing. First derivative increasing means the slope is increasing, means it's concave up. So looking for where the second derivative is positive tells us concavity of the function. And where the second derivative is negative tells the concavity the opposite direction, concave down. And that's, again, as I said, as much as science ever really considers of depth. And so the second derivative test is very tricky. But so our concavity answer to this thing, our part 1, is find the intervals of concavity. F is concave up on the interval from minus 1/3 to infinity. And F is concave down on the interval from minus infinity to minus 1/3. And that's the answer to part B, or part C. Okay. And I don't know if I have space here. Well, yeah. The extreme are easy. Second derivative test is really not hard. It's pretty easy, and it's more valuable when we get to Calc 3 and higher dimensional problems. When your inputs are several different inputs and your output is one, then you're trying to find, well, what's the maximum profit I can get given these costs and these other costs and that sort of thing. Then you're going to have a function that's complex. And so you'd want to use this second derivative test. Really simplifies it. Okay, so not in this class. This class, we're just going to stick to the one-dimensional functions. And so I'm going to use the second derivative test to find the extrema. And so the second derivative test is just f has a max if we look at the critical numbers. So we look at the critical numbers is x equals 1/3. And let's check that one. Second derivative test is just check the second derivative at that critical number. And I just want to know, is it positive or negative? How does it compare to 0? Is it bigger or smaller than 0? And the second derivative at, at 1/3 is one of the critical numbers. Now, what's the second derivative at 1/3? Well, at minus 1/3, it was 0, but at plus 1/3, it's positive. So the second derivative at minus 1/3, or it's at positive 1/3, is positive. I can just stick it into the second derivative here. 6 times 1/3 is 2, plus 2 is 4. So the second derivative at 1/3 is 4, which is bigger than 0. Therefore, f is concave up. So at the critical number, where I may have a max or a min, I've now figured out that the function is concave up. Therefore, f of 1/3 is a max or a min. And again, this is the tricky part. If the function is concave up, if the second derivative is positive, if this function's concave up, it's actually a minimum. Okay, the minimum because it's concave up. So concave up actually means, oh, you think it looks like a smile, it's all happy and positive. No, it's a minimum. Okay, it's at the bottom. The function's at the bottom there. And at the other critical number, x equals minus 1 is the other critical number we found right there. F double prime of minus 1 equals, well, I put in minus 1 here for f double prime, and I get -6 plus 2 is -4, which is negative. So I just care that it's negative. Since it's negative, then the second derivative is concave down. And the second derivative test says if it's concave down at a critical number, then that means f has a maximum. So f of -1 is a max, and I ran out of space. Okay, sideways max, I can't imagine you can read that, but whatever. Okay, so that's the second derivative test. That's what the second derivative means, is that it tells you all about the function's concavity, where it's concave up and where it's concave down. The second derivative is like the derivative of the first derivative. So first derivative tells you where the function is increasing or decreasing. So the second derivative tells you where the first derivative is increasing or decreasing. So where the first derivative is increasing, then the function is concave up. And where the second derivative is decreasing, the function is concave down. Okay, so that's the whole business with the first and second derivative tests. Are there any questions about anything?
I have a question actually.
Please.
So at that last part, part D, you were running those tests to see if those critical numbers were positive or negative. Was another way to check that would be to just see if it's inside those intervals we defined in part A?
Mm-hmm. Yeah. Oh, wait, part A?
Yeah, the one just above part D, where it says f is concave up on interval -1.
Oh yeah, that was supposed to be my answer.
Oh, answer. Sorry.
Sorry about that. Yeah. So yeah, f is concave up. So yeah, you just look. Yeah, you wouldn't. I already did these. Yeah. You're right. It was already done right there. If f is concave up on that spot, and I have a critical number at that spot, so therefore I have a minimum, because it's concave up means it's at the bottom of a bowl. Yeah, so that's exactly right. I redundantly did it more than once.
Okay, all right, thank you.
Okay, anything else? Okay, well, good luck on your homework. Let me know if you have any problems, and well, put it on the Google Docs, and then I'll see you next Tuesday, and I'll do the homework problems that you most request. Okay, thanks a lot. See y'all later.
Have a good day. Bye.